Heisenberg's uncertainty principle states that we cannot simultaneously know both the position and the momentum of a particle with perfect accuracy in quantum theory. Its formula is given by delta x times delta p, which is greater than or equal to h over 4 pi, where delta x represents the uncertainty in the position of a particle, times delta p, which is the uncertainty of the momentum of the particle. And when multiplied together, those two must be always greater than or equal to Planck's constant h over 4 pi. Planck's constant, when divided by 4 pi, is a relatively small value. Hence, in our daily lives, we see both position and momentum by estimation of larger objects. Take, for instance, a car moving along a highway. We can easily spot the position of the car along the road, and based on that, we can decipher its velocity. But for microscopic particles like electrons, protons, and even bosons, the best of microscopes suffer. This is why this principle is studied in the quantum field. To understand this principle, let's take a look at the individual components. The wave-particle duality theory, which was suggested by physicist Louis de Broglie, stated that light has a dual nature. It behaves both as a particle and a wave. Light is made up of particles called photons. The energy of a photon is given by formula E is equal to hf, where h is Planck's constant and f is the frequency. The frequency of a wave can be simplified into velocity over wavelength, which will then give us the formula E is equal to hc over lambda, which is wavelength. By transposing, we see that energy over velocity c gives momentum p, which is also equal to h over lambda, or wavelength. So, the momentum of particles due to the duality is closely related to lambda. And though this was suggested for light, it is applied to all particles like electrons and protons and bosons, etc. Since we saw how particles have properties relating to that of waves, it's a relevant question to ask if they have their own equation also. And actually, they do. The Schrödinger's equation is a very long and fancy equation which tells us how small particles are governed by wave functions. A symbol from that equation is psi, which represents the hills and valleys, also known as the crests and troughs of waves. Psi simply shows us the probability of finding the position of the particle. When psi is 0, that is a straight line on the graph shown, it means that the probability of finding a particle there is 0, therefore saying that the particle does not exist in that region. Psi takes a value when the amplitude is greater than 0, represented by the pink shadings. Therefore, when the amplitude is greater than 0, there is a probability of finding a particle in that region, and the certainty of that probability depends on the height of the amplitude or that value of psi. Going back to the car analogy, since the car is very large, it can easily be spotted. But picture this. You want to determine the position of an electron and its momentum. You cannot see it with a microscope only, and you definitely can't see it with the naked eye. So you decide to flash a beam of light, as seen in the image. When too much light is flashed, the precision of targeting one electron is reduced. Hence, you must use a ray of smaller wavelength for greater precision. However, if the wavelength of a wave is reduced, that is, the length of one waveform is reduced, more waves can be produced in 1 second. Thus, the frequency is increased. The amount of energy generated by that wave increases, and due to the law of conservation of energy, when the ray hits the electron, energy is transferred onto it, causing it to change its velocity and thus change its momentum. So you determine the position of this electron as the light will be reflected off it and back into your eyes. But now the momentum has changed. Consider this in the graphs shown. When the electron is living its daily life, it moves with a constant momentum. Using the theory we learned earlier, that since the wavelength is related to momentum, it shows equal wavelengths. As we know the momentum of the particle is constant, the uncertainty of the momentum is zero. That is, we are very certain about the momentum. We know it. However, since the wave moves with a constant momentum and equal wavelengths, the values of psi or amplitude are the same throughout. That is, the probability of finding the position is the same in each region shaded blue. Therefore, the exact position of this electron is very uncertain. It could exist anywhere. Now, when the high frequency radiation of small wavelength hits the electrons, it transfers some energy onto it. A phenomenon called interference occurs where the wavelengths of the radiation and the electron are superimposed, which means they come together and interfere constructively, causing the amplitude of the electron to increase, or destructively, where the amplitude decreases, as shown in the diagram. Thus, the values of psi of the electron changes. That is, it increases more than before. Hence, the probability of finding the position of the electron is greater, as shown in the green. The uncertainty of finding the position of the electron is reduced, as now we are more certain of its position. However, the momentum or the wavelength changes. The momentum becomes more uncertain. This is the basis of the uncertainty principle. You can never simultaneously be sure of the both things. That brings us to the end of today's video. Thank you so much for listening, and please be sure to subscribe to the Youth STEAM Advisors. I'm certain you would love all their content.